continuous? Are the functions continuous? Remember I said that domain and continuity would kind of go together. So in the last quiz, you had to tell me domain, right? In this quiz, you're kind of telling me conceptually the same thing, but you're wording it differently. So instead of saying what's the domain, and you're looking for problems in the domain and then telling me what those are, now we're answering the question, is it continuous? And basically you're looking for problems in the domain is what you're looking for. So if you look at number 1, there are no problems. That is a polynomial. So a polynomial is going to be continuous. It's just going to be a standard like this one, cubed, squared, x, plus or minus a constant. We're done. It's continuous. It's going to do a little wave somewhere in the middle, but it's going to go from one end to the other. So something like number 1 is always going to be continuous. If you look at number 2 and below that, so the rest of these, those are likely going to have a discontinuity, but not always. So the second type here is a piecewise function. So you're going to do some of those graphing. Piecewise functions can be continuous. Sometimes they're not continuous. All right. So the first thing you want to look is the type of graph that the two are made of. This is a quadratic. This is a linear. Those are both continuous functions individually. So now we just have to make sure that at the point where it changes, that it's continuous. All right. The only way that it's continuous where it changes is if it's the same number. Think about when we graph them. On some of them, we graphed them and it did this crazy loop and then it went straight from there to another graph. Continuous. On others, we did a parabola and then we jumped somewhere else on the graph. Not continuous, right? And so for these, you're just going to plug that number in where they change to each one of them. And if it is the same number, it's continuous. If it's a different number, it jumps, right? And so that's all we're going to do to figure this out. We're going to take this -3 and we're going to plug it into each one of these. So we're going to say -3 squared plus 2 times -3. That's the first one. -3 squared is 9. 2 times -3 is -6. 9 minus 6 is 3. So right here at the point -3, 3, we're going to have a hole because it doesn't include, but we're going to see if the next graph picks up at that exact same point. So we're going to do that to the second one. We're going to say negative, and we're going to plug it in here. -3 minus 2. Well, that's +3 minus 2, which is 1. So this point is going to be at -3, +1. It jumps. It jumps. So on this graph, the left side is moving towards 3. When you get there, it jumps to +1, right? So this is discontinuous, and it is exactly what it sounds like. It is a jump at the point x equals -3. It's a jump, discontinuity, jump. So the first one, he's continuous. The second one, jump at -3. A jump at -3. So if we look all the way down to number 6 here, when I have something that is a rational, just like when I was doing my domain, I'm going to want to factor the denominator, okay? I need to factor the denominator to figure out if I have some issues. And so I'm going to leave the numerator alone. For the denominator, I'm going to say factors of 5 that add up to 6. That's 1 and 5. So you're just doing basic factoring there, okay? Basic factoring. So this clearly has two problems. I'm going to have two places where I have a discontinuity. Does everybody see that? That denominator is going to cause me some problems, all right? The two problems that I have here are when x equals -1, that causes a 0 in the bottom, and when x equals -5. You have two more types, removable. Last year we called them removable and non-removable. This year we call them removable and infinite, okay? Removable means I can get rid of my problem. Do you see one that you think you could get rid of?
Yes.
Yes, I see one I could get rid of with cancellation. I could get rid of my negative 5 problem. I could get rid of him by canceling him out. He cancels out. Negative 5 is considered removable. All right, removable. Then I have one I cannot get rid of. That's clearly the negative 1. He is my infinite. And so those are your 3 types of discontinuities. You have a jump. Typically, those will happen for a piecewise function. That's where you're going to see a jump. You have removable. That's where you can factor and cancel him with something in the numerator. And then you have an infinite. That's where you're going to factor, but you cannot cancel him with anything in the numerator. All right? Remember, our problems are only in the denominator. So I do not care what makes my numerator 0 unless it helps me cancel a denominator, right? I'm only listing my denominator problems. My numerator is just telling me, is it removable or is it infinite? So if you do not know your parent functions, I would recommend you study your parent functions, okay? So you're welcome to get that sheet out because you're going to be using all different types of functions when you do a piecewise. And then when you go on to shifting the functions around, you're also going to use those parent functions, all right? And so when I look at something like this piecewise, the first thing I do is I highlight my breaks, okay? Because I need to get a visual of from this point to this point, and then this point to this point, and then the next point on, right? And so typically I will highlight my breaks. So by that I mean my first break is going to happen, my first change in that piecewise function is going to happen at negative 4. So personally what I do is I then highlight all the way down at negative 4. All right. My next grouping goes from negative 4 to positive 1. So I'm going to highlight at positive 1. And then my next group goes from positive 1 forward. All right, so those are my 3 pieces of my piecewise function. And then I want to try to get a visual of what type of function it is. This is where your parent functions come into play. I know that an x squared is going to be a parabola. I know that just a negative 2 is going to be a horizontal line. That's a constant function. And I know that the cubed function is going to be a little guy like that. So I have gotten a visual of the parent functions, all right? Now I just need to figure out where this happens, okay? Think about your shifting. Let's go to the parabola first, all right? My vertex for my parabola is going to shift. Normally it would be right here at 0, 0, but I have a plus 5 on the inside. So where is it going to shift? Well, inside it's going to go left because it's opposite. So I'm going to go left all the way to 5. This is where my vertex for that parabola is going to be. Here's what I need to know. At negative 4, is it open or closed circle here? Closed. And I know this because it's or equal to. So when I sketch that, I'm going to put a closed circle right there. You can plug it in. Negative 4 plus 5 is 1. 1 squared is 1. So if I plug in my endpoint here, negative 4 plus 5, square it, I'm going to get a 1. So I know that closed circle happens at negative 4, positive 1. And then I'm just sketching the rest of that parabola. There's the rest of my parabola. The next one is a constant function. Well, this is kind of easy because a constant function is a horizontal line at that number. So I am going to have a horizontal line at negative 2 in that center part of my piece. But it's going to be an open circle and an open circle, right? Open and open. So I'm going to go to negative 2. I'm going to do an open circle at negative 4 and an open circle at positive 1, and it's just going to be a constant function. Just a constant function right there. right, the last one is a cube function. So it looks like this. Normally the turning point of that cube is at 0, 0. Inside though, I have a -2, which is gonna move that curve change over to the right 2, right? Everybody see that? So the quote unquote vertex of my cube is gonna look like this. I do need to figure out what happens at 1 because it is a closed circle. So I'm going to plug in a 1 here, 1 minus 2, and then I'm going to cube it. 1 minus 2 is -1. -1 cubed is -1. So at the point 1, -1, I have a closed circle. All right, a closed circle. And then I'm going to do my graph. So my turning point is what I've already graphed here at 2, 0. So it's really just going to do that. So I only have a piece of my cubed function. Normally it would keep going all the way down like this guy does, but it stops here because they told me to. All right, it stops here because they told me to. So this is a piecewise function. This is going to be a jump discontinuity here, a jump discontinuity here. Had they been the same number, it could have been continuous here if this had been the same number and picked up, right? It just depends on what pieces they told you to use. Reminders, as we've been kind of going over it a little bit, you have to remember some things about these. Negative on the outside will flip the graph, right? A coefficient, so a coefficient of the graph of f of x will stretch or skew. We talked about that, right? Stretching and skew or shrinking, depending on what you have there. Absolute value of an integer is going to stretch. Absolute value of a fraction is going to shrink, all right? Inside, if you have a plus or minus inside the function, that's going to move you left if it is positive and right if it is negative. Outside of the graph, it's going to move you up with a positive and down with a negative, right? So those are kind of our rules. You need to know the parent function. These start or turn or whatever at 0, 0 standardly. So then what is happening if I do some stipulations on that particular graph, all right? And so I need to first recognize what parent function I'm talking about. In this case, the one that I've chosen to do here, I'm talking about the reciprocal function, all right? The reciprocal function. So your reciprocal function typically looks like this, with that change in, infinity there happening at 0, 0. And so I have a couple things that are happening here. I have a flip, which means they're both going to flip direction across the x-axis there. And I also have an inside movement. Inside movement. All right, and outside would be plus or minus on the outside of the fraction completely. All right, so I only have a left-right movement here. I do not have an up-down, and I have a flip. So for something like this, where you don't have like a vertex like you have with like an absolute value, I kind of shift my crosshairs is what I'm shifting. So normally this crosshairs will tell me how to draw those little guys. So I'm going to shift it. Inside it's a 3, -3 inside. So which way am I going to go? Inside, I'm going to go right. Outside would look like this. It would not be inside the fraction at all. That would be an up or down movement. That -3 is inside. So my crosshairs is going to move to the right 3. Now it's because it's not moving. So I'm going to kind of do this to get a visual of where I need to sketch that graph. Because I didn't move up or down, my x-axis is still that piece. Had I moved up or down, I would have shifted that little dotted line up or down. It is flipping. So instead of it going down here and up here, this guy is going to flip up and that guy is going to flip down. They're both going to flip across. So my graph is going to look like this. This one flipped up and this one flipped down. That's my reciprocal function. So if you had a parabola, a negative on the outside would flip it down, right? If you had an absolute value, normally a V, it would flip it pointing down, right? And so inside's going to shift your vertex left, right, outside, up, down. And then you're just going to sketch it. So you're not having to worry about specific points. You're just sketching the graph at this point. Really quickly, the next set is basically the same thing, but I give you the function and you give me the answer. So now I'm looking for you to look at the function and then tell me what's happening to it. What is happening to it? I will say, like, number 17 has a stretch and so does number 18. I am not going to give you any stretches on these because that's difficult to then give me the value of the stretch for something like that. It would be easier for an absolute value or even a parabola to figure out the stretch, but I'm not going to give you. I'm really looking for a parent function left and right movement here is what I'm looking for. So don't worry about the stretches. Those just got thrown in there because I don't take as much time when I'm giving you a review as I do on your quiz. So what I'm looking for here is, do you know the parent function? All right. So now we're reversing our brains. I'm giving you a picture and you're having to give me the function itself. So like for number 16, hopefully in your brain, you're like, I know what the parent function is. It does ask for the parent function. So the first thing you're going to have to tell me is the parent function here is the absolute value function, right? And then I'm going to say, now give me the actual equation for the function that you see. All right, which means there's left and right, up and down movement here. So this function, we'll call it the G function, moved left 2 places. So that means on the inside, I need to account for moving left 2 places. Remember, it's opposite. It also moved down 3 places. So on the outside, I'm going to have to account for down 3 places. All right, so all you're doing is parent function, and then how did this thing shift? All right. The only thing I will do potentially on the outside is a flip. All right. So while I may not look for a stretch or skew, if that thing had been pointed down, I would have needed a negative on the outside. All right. I am going to ask you for your axis. I'm going to ask you for your vertex. And I'm going to ask you for your y-intercept. All right. So if we look at the one that I'm at right now, number 20, remember, when it's in this form, it's beautiful, right? It tells you exactly what you need. Your axis is going to be just x equals this number, but remember, it's the opposite of that number. So the axis here is x equals -1. Your vertex is going to be composed of these 2. Again, the h is the opposite because it's minus standard. So -1 and +4 is my vertex. And when it's in vertex form, they don't hand you the y-intercept. You have to figure it out by plugging in a 0. So I'm going to plug in a 0 here. Do my order of operations. So my y-intercept here is 0, 2. And then I'm going to graph it. If I graph that axis, that happens right here. Remember, it's dashed because it's not actually part of your graph. Your vertex is at -1, +4. That's going to be right there. Your y-intercept is at 0, 2. If you have your y-intercept, you can just mirror it across because that's your axis of symmetry. It should be symmetric. This graph is pointing down. I know this because of the -2 in front of it. I don't have to worry about stretching and skewing this guy because I have actual points to plot. All right, so it naturally skews itself because I plotted the points. It naturally pulled that. It is in standard form. your axis is not just h, it is negative b over 2a. He's a little bit more difficult. Or you could complete the square if you want. Your vertex, you've already found your x value. That's the negative b over 2a. Your y value is just when you plug in your x value. That's what y always is. Your y-intercept is handed to you. It is just 0 and c. Remember, this is a, this is b, this is c. All right. So for this one, negative b, well, that's negative 4 over 2 times a is going to give me 4 over 2, which is 2. So my axis is going to be x equals 2. That's going to happen right here. My vertex, well, I already know the x value of my vertex. That's just 2. Now I plug a 2 in. Anytime you have x to solve for y, plug it in. So into my function, I have 2 squared minus 4 times 2 plus 6. 4 minus 8, negative 4 plus 6 is going to give me 2. So my vertex is going to happen at 2, 2, right here. My y-intercept is really easy on standard form. It's just 0c. So it's going to be 0, 6. So 0, 6. I'm going to plot that. Remember, you can just mirror. Goodness gracious, it's just deleting. You can just mirror that over. It's 2 away from here. Go 2 on the other side to mirror it so you can sketch it. It makes sense that this guy's pointed up because it is a positive number in your a value. So we're just going to sketch that graph. So if we're solving by factoring, we're going to set that equal to 0, set each one equal to 0. That means your zeros happen at negative 2 and negative 3. Right? If I couldn't solve it by factoring, I'm going to use quadratic formula.